Hello, hello. Welcome, everybody. My name is Reed Arnold. It is June 12th, 2023. Welcome to another free GMAT prep hour. If you're looking for other free prep materials, please know we have them. You can attend any live or in-person GMAT, live or online GMAT class for free. The first session, you can sign up. No money down. You don't got to promise anything. Attend our first class. That's one out of the 9 classes that you get free of charge. I always tell people you might as well do it even if you have no intention of signing up, because we talk about some important stuff in that first session. So you might as well attend and, be in front of a teacher and ask your questions and get some major strategies for data sufficiency and sentence correction and just general GMAT studying. So just know that those are totally free. You can do a similar thing with our interactive course, our online video course. You can try a sample of that, get a sense for what that program looks like. Really nifty, award-winning educational software program. And also for the last year or so, we've been offering our Foundations of GMAT Math workshop for free. And I'm also excited to announce that lately we've kind of revamped that. We've changed it from 1 7-hour session to 2 4.5-hour sessions. So it's actually more time for you, more free prep for you, but done in a much more manageable size. So that 1 7-hour day was a lot. We've turned it into 2 4.5-hour sessions. You can take them in either order. The computations session will focus on kind of numbers and arithmetic and quick calculations. The variable sessions deals with more like algebra and translation and word problems. Again, order doesn't matter. They're in communication with each other, but you can do any one first that you find convenient. But we hope to see you there. Those are running, once or twice a month right now, sometimes even more than that. So I'll be teaching several of them. My colleague Whit, who helped design them, and you'll also see on the free GMAT prep hours, is a frequent teacher, along with, I believe, Chris Gentry. We have a great team teaching those, so we hope to see you at one of those soon. Tonight, I was just telling the group before the recording started, I feel like we've done so many of these that I feel like I'm kind of running out of stuff to say for this test. And I know I've said that the last few times, but it's more and more true. It's always like, what else can I say that's new and interesting that they don't already have a recording of? And I feel like we do have a video on quadratics. I'll show you which one that is a little bit down the road here. But I do feel like there's maybe a few holes to plug in the quadratic game. So tonight we're going to talk about quadratic equations and how the GMAT tests quadratic equations. Now, one thing I do want to point out early and right off the bat, you might remember from high school algebra 2, the quadratic equation or the quadratic formula, x is the opposite of b plus or minus the square root of b squared minus 4, the discriminant over 2a, all that stuff. Yeah, we're not going to worry about that. This is not the kind of quadratic stuff that you need to know for the GMAT. It does not need to get that deep in the algebra. I can't think of a single GMAT problem where you actually need this formula. So we're going to talk about what quadratic equations are, yes, but we're going to really focus on how the GMAT tests them, because they don't get into all the high school math stuff, just like any math topic on this test. The high school math approach is not often best. You need some basic understanding of the concept, but the old kind of algorithms or the old strategies, the old math problems you used are often going to overlook an important GMAT game that's being played. And that's true with quadratics, it's true with everything else. So let's dive in here. First, let's just clarify what a quadratic equation is. So a quadratic equation is an equation containing a variable raised to the power 2, but not higher. There's no power of 3, no power of 4, no power of 5. I suppose there could be a power of 4, as we'll see down the line, but that's a little bit, that's a tricky version. Mostly you can think of a quadratic as something raised to the power of 2, but not higher. So some examples here: x squared plus 7x plus 10 equals 0, x squared minus 36 equals 0. This here is a very common quadratic. We'll talk about that: x squared plus 2xy plus y squared. This one you might not immediately recognize as a quadratic. After all, where is the power of 2? You don't have a sense where the power of 2 is lurking in that equation? Any guesses in the chat? Where is that power of 2 in this equation? Well, you might see that x in the fraction, in the denominator of that fraction. And my general rule of fractions is get rid of them. I don't like them. They're annoying. Yeah, good, Vivian. If we multiply this whole equation by the unknown variable x, remember, you can do whatever you want to equations as long as you do it to both sides. If we do that, we're going to end up with x squared plus 20 equals 12x. And we subtract that 12x, and we're going to get x squared minus 12x plus 20 equals 0. Now it looks much more like the standard quadratic we are used to seeing. Okay, so you can hide quadratics with algebraic trickery, but good algebra foundations can bring them back. Quadratics have what we call roots, which is just another word for solutions. And when you see a quadratic in this form, we'll talk about how to transfer from one to the other. To go from this version to a quadratic, the standard form of the quadratic, you use what is often called foiling. But I want to be clear what the roots of a quadratic, what that means. The roots of the quadratic are the solutions to the quadratic when it is set equal to 0. And that's an important distinction, as we will clarify here. If we can get a quadratic into this form, what does that tell us about x? And more, why can we say that about x? Some of you might know the answer without fully grounding the why. And in GMAT studies in general, it's always good to get to that, why something is true, not just that something is true. Deeper understanding of these. As I said, the principles don't get that much beyond the core, just basic ideas of these math concepts, but understanding those basic ideas deeply does pay off. Right, we can say from here that x is either 7 or -2. Why? Well, fundamentally, what we have here is some number, let's call it a, times some other number, x plus 2, let's call that b, and we know the product is 0. Well, when is a times b 0? Either a is 0 or b is 0. That's when a product is 0. So either x minus 7 is 0, which means x is 7, or x plus 2 is 0, which means x is minus 2. And these are what we call the roots. They're the x values when the quadratic is equal to 0. There's often 2, but there does not have to be. There could be 1. And technically, there could be 0 real roots. We'll talk about real versus imaginary here in a moment. But just know that the GMAT doesn't actually deal with imaginary not all that much. It never deals with imaginary. So you'll be dealing with quadratics that either have 1 solution or 2 solutions, almost always. Solutions or roots. Now, to go from this equation to the standard form of equation you're used to, you might use what's called FOIL. That's a good way to remember the process here. FOIL stands for first, outer, inner, last. And that's just the order in which you multiply these numbers here. You multiply the first, so you get x squared. You multiply the outer, so you get plus 2x. You multiply the inner, so you get minus 7x. And you multiply the last, so you get minus 14. And you bring all that together and you get x squared minus 5x minus 14 equals 0. Foiling, I understand why it's a thing. I understand why we use it, but I think it's like all we're doing here, sorry about the siren, all we're doing right now is kind of some good old-fashioned distribution, actually. X minus 7 looks like 2 variables, and it is, but you can also express it as 1 variable, a. It's just some unknown a. And if it was some unknown a, we would say it's a times x plus a times 2. And if we plug back in what that a is, it's x minus 7 times x plus x minus 7 times 2. And then you can distribute from the right, x times x, x times 7, 2 times x, 2 times -7. You'll get the same outcome here. So just know that foiling, it's really just distribution. And so that's how you go from, foiling is how you go from an equation in this format to the standard format. And you will do that, no doubt. But of course, you will also have to go from this format back to this format. We'll deal with that here shortly. But before we do that, let's just make a few important clarifications. This is just the same thing where instead of having numbers, our roots are variables. So x is either a or b. I think one thing I'll ask here is, imagine if a, what if a is negative? Can a be negative? Does that change anything about how we'd write out our quadratic to find these roots if a were negative? Or would we leave it as x minus a? Yeah, good, Xana. It would stay the same. You don't, so there's an instinct like, oh, well, if it's a minus, it's minus a, but a is negative. Let's turn it to x plus a times x minus b. I understand why you're thinking that, but that actually changes the answer to x. Is the root is now the opposite of a if we turn this into x plus a. So note that these variables can be negative. It's just that when a variable is negative, the minus sign is part of the letter. That's the tricky thing about negative variables, right? -7, the symbol we use for that is a negative times a number. In fact, we can rewrite it as -1 times 7 if we want. But for a variable, when we say, you know, this is a negative number a, there's no minus sign outside of it. It's all contained in that variable. So this is still the kind of standard form to find the roots. If, you know, if you have a negative answer, you can think of it as x minus -7, for instance, times x minus 2. Right here, your roots are -7 and 2. Now, a common mistake I see, and it happens with equations, but it really happens with inequalities, although the mistake is really identical. Let's say I have this inequality, x minus 3 times x plus 2 is 6. Can I say x is greater than, I'm sorry, x minus 3 times x plus 2 is greater than or equal to 6? Can I say x is greater than or equal to 9, or x is greater than or equal to 4? Am I allowed to do that? Vivian, I see your question. We'll go back to that and dig into that a little bit more in just a moment, because it is an important distinction. So if x minus 3 times x plus 2 is greater than or equal to 6, can I say x is greater than 9 or x is greater than or equal to 4? What do we think? Yes or no? Any answers from the chat? Any instincts? Let's start with the equation format. If I have x minus 3 times x plus 2 equals 6. Looks pretty similar to what we had before. You know, product equals 0 here, product equals 6. But remember, we can rewrite this as some number times some other number equals 6. So if some number times another number is 6, does that mean A is 6 or B is 6? That doesn't hold. I can, for instance, you can do 3 times 2. Neither of the numbers is 6, but the product is 6. So you can't say that one of these numbers is 6. You can't say that x is 9 or x is, what would it be, 4. Notice if x were 9, you would have 9 minus 3 is 6 times 9 plus 2 is 11. So you'd have 9 times 11 is 99. That's not 6. This only works, this product rule only works when the product is 0. Because again, that's the product. 0 is a special outcome of a product because you know one of the numbers in the product is 0. That's not true with 6. That's not true with any other number. Only 0, only a product that results in 0 means that one of the numbers was actually 0. So in this equation, you couldn't say that one of these is 6 and solve for x. You'd have to FOIL it out and then subtract 6 and then factor it back. And in the inequality, we can't say that x is greater than or equal to 9 or x is less than or equal to 4. If a times b is greater than or equal to 6, same thing if b as being equal to 6, right? That doesn't mean a is greater than or equal to 6 or b is greater than or equal to 6. So it's not true with numbers, not true with single variables, it's not true with these either, because these are ultimately, you can rewrite them as single variables if you so choose. So that's a big no-no. It's not an uncommon problem I see. It's not an uncommon mistake students make. But the quadratic, in order to do anything with it, you really need to set it equal to 0. I would also add that quadratics mixed with inequalities are almost always a bummer. But if you have to do it, get the 0 over here. So, you know, FOIL this out. So you have x squared minus 3x plus 2x is minus x. Minus 3 plus 2 is times plus 2 is minus 6 is greater than or equal to 6. And then I'm going to subtract 6 from both sides. And I'm going to say x squared minus x minus 12 is greater than or equal to 0. And then I'll factor this back. We'll talk about that in a moment, but it would end up being what? X minus 4 times x plus 3. Is greater than or equal to 0. But I will note that even here you can't split this up into x is greater than or equal to 4 or x is less than or equal to x is greater than or equal to -3. Quadratics and inequalities are just not much fun. So just be careful with them in general. But if you're going to do anything with a quadratic, make sure it's like algebraically, get it equal to 0 first. Any questions about just the basic setup of roots and solving? Oh, Vivian, your question. Yeah, let's go back to this question here. So let's go to the x minus a and x minus b. So Vivian said, wouldn't x minus a, so x minus a negative number, doesn't that equal x plus that number? And this is kind of what I was trying to capture earlier. Not really, because again, that number is a negative number. So x minus a negative number can't also be x plus that negative number. If we do x minus a negative number, like x minus a, where a is less than or equal to 0, or let's just say a is less than 0. Yes, I am subtracting a negative, but I don't want to turn this into x plus a, because whatever a is itself. If a is negative, the minus sign stays in a. It's just not visible. Right? Let's say a is -7, right? X minus -7 does not equal x plus -7. Because I know it equals x plus 7, right? But this is a. The whole thing is a. If it has a minus sign, it's hidden inside it. So you don't want to change the sign because of that. Another common, it's one of those like common error. It's one of those common errors that people don't talk about a lot. It's not like super common, but it's common enough that, you know, it registers for me. So keep an eye out for that with any variable and any problem. Just know that negative variables keep the minus sign contained. You can't see the minus sign in them, so therefore you can't change a subtraction into plus like you can with x minus -7. Here, because we can break that minus sign out, yeah, we can turn that into x plus 7, sure. But that's not the same number as that. Right, we've actually changed that. All right, any other questions about anything so far? Man, these clocks always go so much faster than I think it's going to. We've only just begun. It's already 25 minutes in. All right, let's talk about factoring quadratics. So we talked about how to go from the roots to the standard quadratic. Now let's talk about how to go from the standard quadratic to the roots. And you all might remember this, but let's just really clarify it. I will also note that you might remember that the standard form of quadratics is ax squared plus bx plus c. It is super, super rare to see a quadratic that does not have an a value of 1. You pretty much always deal with just a standard x squared for the quadratic. So I'm not even going to talk about what happens if there's not a 1 here. It's almost always that. In your high school math, you had to worry about other examples. Here, it's just going to be this. And so what you're going to look to do is you're going to think about numbers that multiply to this number, the c value in the x squared plus bx plus c game. But they're going to add to this number. And I'm just going to spoil this for you. The GMAT is not going to give you, by and large, there are some exceptions to this and very hard questions. But the GMAT's usually going to give you quadratics that factor pretty nicely, pretty clearly. You're not going to have to deal with like really hellish, complicated situations where there's all sorts of numbers to deal with. What I look for, I typically get the factors of that c value. So I have 1 times 12, and I try to build a positive 4, right? Is there somewhere to get a positive 4 out of these numbers? 1 times 12, no. 2 times 6, yeah. I can get a positive 4 out of that. -2 times 6 gets me a positive 4. 3 times 4 does not give me a positive 4. -2 times 6 gets me the positive 4 I want. So I would factor this into x minus 2. Sorry, that's -2 times, yeah, -2 times 6, excuse me. So that's x minus 2 times x plus 6 equals 0. So you want the factors of the C value to add up to the B value in some way. So take a minute here, minute or two, and just try practicing on these quadratics using that strategy, right? Think about the factors of this number and find ones that add up to this number. Keep in mind with that minus X, what that number really is. I'll see you all in about a minute and a half. Ten more seconds. All right, so whenever you just see a minus X or a plus X, just know that there's a 1 there as well, right? Minus 1 times X. So I need two numbers that multiply to -12 and add to -1. So that's going to be X minus 4 times X plus 3 equals 0. I need two numbers that multiply to 20 but add to 9. That's going to be X plus 5 times X plus 4. And I need two numbers that multiply to 10 but add to -7. That's going to be X minus 5 times X minus 2. Notice that in choosing these, I try to come up with the three scenarios you're going to see. You're either going to have a plus and a minus here. And you can, right, I could do X plus 3 first if I want. What does that result in? That results in a minus here. Actually, I say that it could result in a plus there. Right? Yeah, because if it was X plus 4 times X minus 3, it would be big enough that this would be a plus, but it'll definitely result in a minus here. The other two have the same sign, so they're always going to be a plus in that last column. Right? We have a positive, positive, and a negative times a negative. But notice the positive, positive is guaranteed to result in a positive, and the negative, negative is guaranteed to result in a negative. The only one that's not sure is this one. And it depends which one is larger, right? If I had X minus 4, for instance, or X plus 4 times X minus 3, and I refactor that, we'd have X squared plus 4X minus 3X, so plus X minus 12 equals 0. So again, a negative C value, but in this case, a positive B value. Any questions about basic factoring of a quadratic before we jump to a word problem? We'll really let this lesson kick off. All right, let's put it to the test here. Take 2 minutes here for a GMAT-like word problem. It's not from an official source, but it's similar to ones that are. So take 2 minutes, send in an answer if you get it. Let's see how we do. That's 2 minutes. I don't see any answers in yet. All right, that's 2.5. Let's call it there. Hard question, especially if you take a certain path on it. We'll talk about the different paths you could take. First thing, let's set up the equations we can pull from this situation. If a stamp collector bought a number of stamps for $100, and perhaps I should have specified that was $100 total, not $100 each. Hopefully that was clear. If they bought the stamps for $100 total, what equation could I build from that information? By the way, if you are watching the recording and you had thought $100 was $100 per unit because I hadn't clarified, pause and retry, having clarified that that's what the 100 stands for. Those of you that are in the room, sorry if I wasn't clear enough. That was my fault. Yeah, good, Kunal. So I could say n times c, where n is number, c is cost. Sure, let's just use it. That's fine. So the number times the cost is 100, where n is the number of stamps and c is the cost per stamp. Well, then 5 stamps are added to his collection, and the other stamps are sold for $2 more than he paid for them. It's a little bit of a trickier situation, but it's back to the standard. All these equations are a form of price times quantity equals revenue or cost, however you want to say it, revenue or cost, depending on which point of view you're looking at. The first situation was n times c. Yeah, good, Kunal. Well, now I'm going to sell 5 fewer stamps because he keeps 5 of them, and he raises the price for $2. So c plus 2. And he makes $20 profit. So careful here. This is one little trap. It's not equal to 20. It's equal to 120. Because he made $20 profit, that means he made $120 revenue. Make sure you're clear which which numbers which in a revenue cost profit game. If you messed up this translation, by the way, and you're watching the video, pause and see if you can carry from here. All right, now things get kind of gnarly. I'll show you what we could do. And I think it's gonna be very clear why at the end of the day, it's not what we maybe should do. We want what he paid for each stamp. So we want C. This is the variable we are solving for. So I want to get that alone. I want to get C equals something. And I have N and C. So let's set up our situation with the substitution to get N equals C. I'm sorry, to get C on its own. If N equals 100 over C, which is just by dividing both sides of this equation by C, I can substitute in 100 over C minus 5 times C plus 2 equals 100, or equals 120. And I don't like how this looks, but it is correct. And now I FOIL. I did what we did earlier. It's just kind of gross. Well, 100 over C times C is going to equal 100 times the outer. It doesn't really matter what order you do this in, but times the outer is going to be plus 200 over C. Times the inner is going to be minus 5C. Times the last is going to be minus 10. That's going to equal 120. And I could subtract the 100 from both sides and be left with 20. I can add the 10 to both sides and have 30. And so I have 200 over C minus 5C equals 30. This is all really annoying, but if I'm in the thick of it, what else can I do? Well, this might look like something we saw earlier, right? We have that variable in the denominator and that variable up here. So let's multiply everything by the variable. And that 200 over C is going to become 200. And the 5C is going to become minus 5C squared. And the 30 is going to be 30 times C. Now, if I recognize that everything is a multiple of 5, let's just multiply everything by 1/5. And I get 40 minus C squared equals 6C. And now I want to get my C, I want to get it all on one side, so I want it to equal to 0. And I really would prefer this C squared value to be positive. So let's bring everything over here, and we're going to get 0 equals C squared plus 6C minus 40. And now I have a quadratic that looks like one we've seen before, and I can factor it. I need two numbers that multiply to negative 40 and add to 6. And those are going to be C plus 10 times C minus 4. Which means C is either negative 10 or 4. And a price of negative 10 doesn't make sense unless someone is really wanting to get rid of some stamps. But on the GMAT, prices are never going to be negative. So the answer here is 4. Okay. Scale of 1 to 10. How do you feel about that process? Did you write positive 10 by accident? No. What positive 10? This should be positive 10. That's supposed to be positive 10. The solution is the negative 10. But in the parentheses, it's gonna be positive. And that's another thing to keep track of, right? These are not the solutions. These get you to the solutions. Don't mix up which step you're on. Okay. I made this question earlier and was doing it while the clock was running, and I finished in 2 minutes, but right at 2 minutes. And I was moving smoothly. I was doing every step as perfectly as one could do it, just to see if I remembered how to do this algebra. And it's doable, but gosh, is it nasty. And I'm just going to say, everybody, if your GMAT work looks like this, if you finish a GMAT problem and you get the answer right, I don't care, and your work looks like this, just lines of math, I assure you, you have missed something. You've missed a better method. It might not be the classroom method, but it's a GMAT method that is better. You don't get extra points for algebra. Now, full confession, every time I take a test, sometimes I only see the classroom method. And so, yeah, I'm just like, well, shoot, I'll just vomit out the math. I know I can do it. It's a pain, but I'll do it. It happens. But when you're studying, you want to find better approaches if you can. And so one of the major things I want to point out today is that quadratics and back solving are very good friends. In general, quadratics and other GMAT strategies besides algebra are very good friends, but back solving using the answer choices really is something you want to be on the lookout for. If you set up these two equations and you get number times cost is 100 and number minus 5 times cost plus 2 is 120. If you set up these two equations, you probably have a sense of like, ooh, this is starting to feel quadratic-y, especially this one on the right. That really looks quadratic-y. I'm just going to suggest that see if you can do something besides quadratic algebra. See if you can do some back solving. Let's use our answer choices. Let's say, right, we have a price and a quantity of stamps originally. Let's start with D, just because it's the wrong answer. We know B is the right answer. Let's say it's $10 a stamp. Well, then we know that the stamp collector bought 10 because it needs to be $100 spent up front. And honestly, if the numbers are this easy, and they are pretty easy, I'm kind of a fan of like, don't even think about, a lot of people are like, which one should I start with? Should I move up or down from this one? If they're easy, just vomit out the whole situation. Here are my 5 different answer choices. Here are my 5 different quantities based on those answer choices. They need to multiply to 100. Okay, well then what happened? We lowered the price, or we raised the price by $2. So here's what that's going to be. 4, 6, 7, 12, 27. And we sold 5 less, so we have Q minus 5. So that's 45, 20, 15, 5, and -1. Well, that doesn't make sense. I'm already done with the last one because I can't sell -1 stamps. So this one's out. And I need one that gets me to 120. So I made $20 profit. Which one is it? This one. 6 times 20. There it is. So this is the answer choice that keeps everything consistent. The answer is B. If the numbers are really simple, just set up a table and just vomit out the situations. The arithmetic's not going to be that bad. You cannot tell me this isn't easier than that algebra I showed you. I just don't believe you. It might not be what was most natural. It might not be like the first thing you thought of. But this is so clear, right? The prices, these are given to us. We get the Q because it needs to multiply to 100. We get the new price by adding 2. We get the new quantity by subtracting 5 from these numbers. Whatever. And then see which one multiplies to 120. Done. B. Quadratics and back solving are very good friends. I'm glad you like it, Kunal. Yeah. Back solving in general is something you want in your pocket. There are certain signs to look for. Nice, easy answers, quadratics, word problems in general. See if you can back solve. All right, moving forward here. Take a look at this question. x minus 7 root x plus 10 is 0. How do we handle this? This seems different, right? Quadratics were an equation containing a variable raised to the power of 2, but not higher. There's no power of 2 in this equation. Or is there? See if you can find the hidden power of 2. Because there is a variable somewhere in this equation that is raised to the power of 2. That variable is this variable x. But how is that variable raised to a power of 2? Well, x is the square root of x squared. So the variable raised to a power of 2 is the square root of x, which again, we're allowed to just call a. And then x will be a squared. So I can rewrite this equation as the square root of x squared minus 7 root x plus 10. And I can factor it just like I did before. I think it's actually the same equation we had. I can say that this is root x minus 5 times root x minus 2 equals 0. And this is one of the GMAT's favorite games with quadratics. They like to hide them. They like to give you an equation where there's a quadratic hidden in it. Part of the job is finding it. So if x and root x, right, if that's a hidden quadratic relationship, try to just spend a minute and see if you can think of other numbers or other variables that could be hidden quadratic relationships. How else could they make it unclear that there's a quadratic in the problem you're looking at, where it might not be your immediate instinct? Here are some I thought of. This is hardly an exhaustive list. There's infinite of these. But each on the left is the x value, and each on the right is the x squared value. Just different ways of hiding this relationship. I guess I could have put negative exponents as well. I could have put like x to the negative 3, and then over here, x to the negative 6. That would have been maybe tricky. But you're looking for this relationship, a number and the square of that number. Just make sure you see how every number in the right column is the square of that corresponding number on the left. So you could build a quadratic equation out of these appearances. All right. Moving on up. So we're about to do 2 questions at once. So I'm going to step away for 4 minutes, give you 2 minutes a question, which is GMAT pace. One of these questions will be data sufficiency. For those of you in the room that are not familiar, or for those of you watching the video, if you're watching the video, I'd pause the video and do a little reading on data sufficiency up front, just so you know what kind of question you're dealing with. But the general idea is that you're not so much trying to answer the question that is asked, you're trying to say where in these 2 statements is there enough information to answer the question that is asked. It's a subtle difference. And you'll always have these answer choices. They'll always be in that order. We use this box here on the bottom right to summarize and synthesize those answers. Okay. So one of these questions will be data sufficiency. So you'll try to decide where there is enough information for an answer. I'll put the answer choices here so you can see them. Go ahead and take 4 minutes and send answers if you have them. All right, gang, that is 2 minutes. Let's take a look here first at this data sufficiency question. Go ahead, send in an answer if you have one. We want to know how many real roots does the equation x squared plus bx plus c equals 0 have? Well, first off, the possible answers to that question are 1, 2, technically 0, although the GMAT's not going to deal with 0 hardly ever. And again, I say hardly ever, kind of suspect never. I've never seen a question that deals with non-real roots. And this, well, let's maybe start with statement 2. B plus C is 15. Actually, no, let's start with statement 1. It'll be easier to start with statement 1. It'll be clearer why statement 2 is what it is. Statement 1 tells me B equals 2 times the square root of C. And it is also worth knowing we are told that these are all positive integers. So there's no worrying about fractions, there's no worrying about negatives. These are positive integers. So I always write that if it's given, because it's usually important. All right, pause int. So B equals 2 root C. Now keep in mind, we're not trying to say what are the roots of the equation. We're trying to say how many roots there are. Now B equals 2C seems like there's not a lot of information there, right? Because there's still 2 variables. I don't know what P and C are. Seems like there's infinite possible cases. But one important data efficiency tactic, and if you don't know this tactic, you should definitely watch up some videos on it that we have on our free prep hour library. Testing cases. Test some cases that fit this rule. And for B to be an integer, root C must be an integer. So we need nice perfect squares for C. So let's say like B is, well, let's say C is 4. So B is 4. So we'd have x squared plus 4x plus 4. Equals 0. Or maybe you could do C is 9. So square root of that is 3 times 2 is 6, and B is 6. You could have x squared plus 6x plus 9. Equals 0. These equations, have you all seen anything that looks like these equations before? Those of you at home watching the recording, do these equations spark any familiarity? Maybe we can do 16, and then B would be 8. We could say x squared plus 8x plus 16. If you tried to factor any of these, what you're going to find, okay, well, I need 2 numbers that multiply to 4, but also add to 4. Well, that's going to be 2. So this is going to become x plus 2 times x plus 2. Here I need 2 numbers that multiply to 9, but add to 6. That's going to end up being x plus 3 times x plus 3. You might notice a pattern already. Here I need 2 numbers that multiply to 16, but add to 8. That's going to be x plus 4 times x plus 4. And all of these equations, all of these quadratics actually only have one solution. In this top one, it's -2. Here it's -3. Here it's -4. And so statement one, you're actually going to, this is going to end up being sufficient. If B equals 2 times root C, turns out there's only going to be one solution to that quadratic. Now, you don't know what it is, but that's not what they ask. They didn't ask what is the solution. They ask how many are there. And there's only one in all of these. And that's the answer to the question that is asked. There's one solution. These are a form of one of the special quadratics. We're going to show you exactly what the special quadratic is here in a minute. You just know that this is a secret sneak in of special quadratics that the GMAT uses with some regularity. Statement 2 tells us that B plus C is 15. And that gives us a lot of leeway. So we could do x squared plus, I don't know, 10x plus 5, maybe. That'd be kind of weird. 14x plus 1. 12x plus 2. Two numbers that add, maybe 2x plus 12. No. It's hard to get perfect integers with this case. 5 and 9. No. 6 and 8. You could do 4 and 2. That would work. So you could do x squared plus 6x plus 8 equals 0. And you could get 2. If you factor that, you're going to get x plus 4 times x plus 2. So 2 solutions to that quadratic. But you could also do this one. You can do x squared plus 6x plus 9, which has only one solution. So this statement is not sufficient. The first equation we build has 2 solutions. This one only has one solution. I am not sure, for the record, that this is a realistic GMAT question. Full disclosure, I made it up. It might be unfair. I don't know if the GMAT would exactly use it. I think the first statement's probably fair. The second might be fair, I'm just not sure. Madison, how to get that first equation? I kind of just guessed and checked it. Oh, also it's wrong, so yeah, never mind. I guessed and checked it incorrectly. Because 6 plus 8 is not 15. 6 plus 8 is 14. So I broke the rule. Yeah. We need the B and the C to add to 15. So multiplies to 12, adds to 3. No. Multiplies to 10, adds to 5. Multiplies to 9, adds to 6. Well, that's the one that's here. This is the multiplies to 9, adds to 6. Multiplies to 8, adds to 7. Multiplies to 7, adds to 8. That one you can do. X squared plus 8x plus 7 is 0. So here that's going to be x plus 1 times x plus 7. There you go. So here we have 2 solutions, and that's just by kind of running through the possible B plus C's that add to 15. So this has 2 solutions. This has 1 solution. That would be insufficient. You could probably also make an equation that had no solutions, but again, the GMAT doesn't really expect you to know how to formulate or think about quadratics that have no solution, so I wouldn't worry about those. Again, I don't know if this is fully realistic, but I'm just trying to build up our quadratic muscles, so I'm okay being a little bit fast and loose with how the GMAT would actually test the subject today. I think this first one is very fair. This first equation is a very fair quadratic trap that they could set, where it doesn't feel sufficient at first, but if you actually build it out, it turns out that every situation only has one solution. The problem-solving question that we had, again, dealing with two real integer solutions. We want the largest possible value of k. Well, if you try to do 20, x squared, answer the previous question was A, Vivian. The first statement was sufficient, the second one was not. If we try to do x squared plus 8x plus 20 equals 0 on this equation, so we need two numbers that multiply to 20 but add to 8. And they need to be integers. And you're not going to find any. There's no numbers that multiply to 20 that add to 8. Not positive 20 and positive 8. So 20 is not going to work for this one. If you try 16, x squared plus 8x plus 16 equals 0. You need two numbers that multiply to 16 and add to 8, and you might recognize that that's, oh, I can do 4 and 4. This is, again, one of the common quadratics that gets tested, but this only has one real solution, -4. That's the same solution twice, which really folds into one solution, so we don't have two real solutions, so B is out also. We're going to find our correct answer at C, x squared plus 8x plus 15 equals 0. So I need two numbers that multiply to 15 and add to 8. Well, that can be x plus 5 times x plus 3. So we have two real solutions. They're both integers. 15 is as big as we can make that k value and still have two real solutions. So the answer here is C. And that's, again, by kind of plugging and chugging with the answers. I don't know how to do this algebraically. I guess you'd have to think about, I guess you could think about, you need two positive numbers that add to positive 8, and you want to make k as big as possible. So what two numbers add to 8 that multiply biggest? And 4 and 4 would be, except they have to be two different ones, so you then have to say 5 times 3. So you can kind of reason your way to 5 and 3 as well. Can you please explain why A is the answer to this previous question? Because statement 1 was sufficient and statement 2 was not. Statement 1 tells us there's only one. So if we run through the cases, and I'll stop. I'll do this later after the recording, because I don't want to run through it again for the recording. But yeah, just stick around after, and I'll explain why statement 1 is sufficient. But it's just a testing cases game. / a recognition that statement 1 brings in a special quadratic. These are the three special quadratics that the GMAT uses with some regularity. We just saw several examples of this one. The last two questions dealt with x plus y squared. You want these on flashcards, you want these memorized. I'm not going to spend a lot more time digging into them because we actually have a video that already does a lot of work with those special quadratics. This is the other quadratic video that we have up already in our library, Quadratic Patterns, taught by Dimitri. It's a great video. It really digs into, different ways to be aware of, recognize, and use these special quadratic formulas. So seek that out if you want more practice with those. But these are the common formulas that the GMAT will use. And I said hiding special quadratics. Everything we talked about earlier with hidden quadratics, you can use with the hidden special quadratics. You can use the same relationships, the same variables to hide a special quadratic that you would use to hide a regular quadratic. So I might do, for instance, something where you might see on a question 5 to the 10th. That's too big. Let's do 5 to the 6th minus 3 to the 6th. Well, 5 to the 6th is 5 cubed squared. And 3 to the 6th is 3 cubed squared. So we can turn this into 5 cubed minus 3 cubed times 5 cubed plus 3 cubed, which is 125 minus 27, so that'd be 98, times 125 plus 27, which is 152, I think. Not the cleanest numbers, but you could factor them down from there. So they like to hide these quadratics, just like they like to hide other quadratics. All right, we're going to do 2 more questions, everybody. One of them a tricky problem solving. Go ahead here, take 2 minutes. Okay, that is 2 minutes. Final guesses. If you're at home and you're watching a recording, you feel free to pause and keep working, but let's dig into this one. This is tricky. But again, the GMAT, it's like, this is not the kind of question you dealt with in high school algebra, quadratic math, but it does feel somewhat like a GMAT problem here. I think there are a few solid ways through this, though. Let's kind of go through all of them. Well, first, let's just think about what this means. 5 is one of the roots of the quadratic. What does that mean? That means 5 is a solution to this quadratic. X could be 5. Now we know X could be something else, but X could be 5. It does make the equation work. And so that means we can plug it in. And we can plug 5 in and say, okay, that means 25 minus 5 times B minus C equals 0. If I do a little rearranging there, I know that 25, and I think I can type these out. 25 is going to equal 5B plus C. Or, just to write that, 5B plus C is 25. And what else do I know? I know B plus C is 17. And now I'm actually out of quadratics and I'm into linear equations. These are just two linear equations that I can solve as I would any linear equation. I think it's easiest here to just subtract that bottom equation and say 4B plus 0C, because C minus 0 is 0C, equals 8. And so then I can say B is 2. And once B is 2, C's got to be 15. And so then I can plug those into my quadratic. X squared minus 2x minus 15 is 0. And I need to factor now. Two numbers that multiply to negative 15, but add to negative 2. Well, that's going to be x minus 5. Which, by the way, I already knew 5 was one of my roots, so that makes sense. So x minus 5 times x plus 3. And so the other root here is negative 3. So it's just by remembering what root means. It means solution. That means it should go into the equation, no problem. Do that, make it go. Then you can solve for B and C with the two equations you get. Plug back into the original quadratic and factor. You're going to realize x is 5, which you already knew, or negative 3. So that's one good way of doing this problem. I think another good way is to recognize that, okay, x minus 5. I know if x is a solution, then I know that my equation is going to take the form somehow x minus 5 times x minus my other root. Whatever that other root is. And if you want, you can plug in the different situations you have. You can plug in these other roots. This is a back solve. Remember, quadratics and back solving are good friends, right? If I plug in 5, then I'm going to get an equation x squared minus 5x minus 5x plus 25. So that's going to be x squared minus 10x plus 25 equals 0. Well, in this case, my B value is negative 10. And my C value is 25. Those don't add to 17, right? These need to add to 17. So A is out. I could try 3, x minus 5 times x minus 3. What does that give me? X squared minus 5x minus 3x is minus 8x. Minus 5 plus 3 is plus 15. Negative 8 plus 15 does not equal 17. So let's try 0. X minus 5 times x minus 0. Well, that gets me x squared minus 5x minus 0. Yeah, so that's just this. So plus 0, I guess. That does, there my B is negative 5 and my C is, or my B is 5 and my C is 0. 5 plus 0 is not 0. If I try negative 3, x minus 5 times x plus 3, x minus minus 3 equals 0. If I FOIL that out, x squared minus 5x plus 3x is minus 2x minus 15 equals 0. Here my B is 2 and my C is 15. There you go. 2 plus 15 is 17. So it has to be D. Now, is that, it's a little bit grindy. It's a little bit just like, I'm just going to vomit out the different, I'm just going to FOIL a bunch and see which one gets me a B value and a C value that add to 17. All right, 5 and 0 do not. 8 and 15 do not. 10 and 25, I highlighted negative 10, but really it should be 10. Because notice it's minus b, so 10 and 25, those don't add to 17. But 2 and 15 sure do. That's another good way of doing this. Kind of work through your answers here, just make it the other root. I think there was one other way of doing this. I think this is the most like algebraic way. We think about x minus 5 being a solution. And then the other solution is x minus, I don't know what it is, a equals 0. Now I'm going to solve for a. Well, I'm going to get x squared minus 5x minus ax plus 5a equals 0. This is tricky, but this would be plus a. Yeah, this is a tricky example, but you have to say plus a negative 5a equals 0, because you need this to be a. Oh man, that's hard. Yeah, this is dealing with that negative variable that we dealt with earlier. But plus a negative 5a will turn into plus 5a. Why? Hold up, no, excuse me. It should just be minus 5a. And why did I do that? Because I want a c here. I want minus c. And I want minus b. So I want these two things to be minuses. Minus bx minus c minus bx minus c. And this is tricky. This is by far the trickiest way. So no worries if this is like spinning in knots, because I had to really fight to get it myself. I know now that this number, which is b, plus this number, which is c, equals 17. And so 5a plus negative 5a is going to be 5 minus 4a equals 17. And if I solve for a, which is what I want, I'm going to get a is minus 3. Subtract 5, divide by negative 4. So 3 different ways of doing this. This last one I think is the most abstract and hellish. And it's another good example of like, don't try to do pure algebra. Use your answers, right? Plug in the answers and FOIL, or plug this into the equation and just know that it works because it's a solution. Don't try to just do pure, math class stuff, because that gets abstract and tricky real fast. Be more strategic around the concept rather than trying to, gung right into like the purest math of the concept. Last question here, and then we'll wrap up. I know I went a little long, but I wanted to get through the full problem set today. And I want to just spend some time here talking about the connection between quadratics and graphs, because it does show up on the test. So take 2 minutes. Is another data deficiency. Which statements, if any, are enough to answer the question that is asked? And remember the 1210 mnemonic. All right, that is time. So certain questions do deal with the basics of the graphs of a quadratic, not nearly as much as you did in high school, but some certain phenomenon sneak in. And I'll just let you know what the phenomenon is. They're often dealing with the connection of the intercepts on the X and Y axes, the variable C in the standard form of the quadratic, and the variable B in the standard form of the quadratic, because these variables all relate actually underneath. They all kind of relate to the intercepts of the X and Y axes. And we'll specify how shortly. But first, let's just think about this question here. We want the y-intercept of the graph. Well, what do we know about y-intercepts of graphs? They are where x equals 0. And so we want the y-intercept of this graph. We want to know when x equals 0. And if we plug that in, it turns out that C is the y-intercept of a quadratic. That value C tells you the y-intercept of a quadratic graph. And so we want to know what is C. Statement 2 tells me the product of the x-intercepts is 0. Well, what do we know about the x-intercepts? That's where y is 0. Now, first, this doesn't feel sufficient, right? But if y is 0, then that means that 0 is x squared plus bx plus c. I want to know what c is. And I'm told the product of the x-intercepts is 0. Well, what are the x-intercepts? That's where y is 0. And where y is 0, what have we seen we can do with quadratics? We can factor them. We can solve them somehow to be in the form x minus 1 solution times x minus another solution. So this means x is m, or x is n, when y is 0. It turns out this whole time when we've been talking about roots, when we've been talking about the solutions to a quadratic equation, we've also been talking about the x-intercepts, the places where the graph of a quadratic crosses the y-axis. The x-axis. That's what the roots are. They're where the graph crosses the x-axis when y is 0. And so I don't know what these two roots are, but I know they multiply to 12. Okay, but we didn't want the x-intercepts or the product of the x-intercepts. We want to know what the y-intercept was. Well, if we take this factored form of a quadratic and refoil it out, we're going to end up with x squared minus mx minus nx plus mn. And with just a little rearranging, we have x squared plus, or let's say, let's say plus negative m minus mx, negative m minus nx plus mn. And it turns out, if we look at the original standard form of the equation, here is my b value, because it's the number multiplied by x, and here is my c value. I know mn is 12. That is my c value. The y-intercept is the product of the x-intercepts, which is pretty surprising. I think. C equals the product of my two roots. And so even though I don't know what they are, I don't know if it's 3 and 4, I don't know if they're 2, 6 and 2, I don't know if they're -6 and -2. But all of those graphs cross the y-axis at 12, right? If I do x minus 3 times x minus 4, those are going to cross the graph. That crosses the y-axis at 12. If I do x plus 3 times x plus 4, so now my x-intercepts are -3 and -4. That also crosses the graph at 12. If I do x minus 2 and x minus 6, that crosses the y-axis at 12. X plus 2, x plus 6, that crosses the, I'm sorry, x plus 6, yeah. That crosses the y-axis at 12. So the y-intercept is the product of the x-intercepts. This statement is sufficient. So it's either going to be A or D. Because once statement 1 is sufficient, you know that it's not B, C, E. Statement 2 tells me the sum of the x-intercepts is 8. And so that's m plus n equals 8. Well, using this same kind of formulation here, that could be x minus 4 times x minus 2, and my y-intercept will be 8, or it can be x minus 6. I'm sorry, it should be x minus 4 times x minus 4. And then the y-intercept will be 8, or it can be x minus 6 and x minus 2, and then the y-intercept will be 12. C is, sorry, I said 8. C is 16 in this case. So the y-intercept is 16. Here, the y-intercept is 12. You have different answers. This is not sufficient. The answer must be A. But notice the sum of these. If I just multiply by -1, negative m minus n is -8. Notice that also lurks in this equation here, in the standard form of the equation. The B value is related to the x-intercepts. It's built out of the sum of the x-intercepts. Now it's made negative. You don't need to understand this specifically, but just know that the connection is there. I think that's what I stress. Is that the sum of these x-intercepts gives you the B value, and the product of the x-intercepts gives you the C value for the graphs that the GMAT deals with. And that's a little bit surprising and not often fully stated, but there is this connection here. And we can kind of think about it, because on the GMAT, you're only going to deal with quadratics that open upward. That's another thing you might remember from high school, is if there's a negative x squared, the quadratic is frowny, but we're not going to deal with that. We're only going to deal with positive x squareds on this test. And so if we have a positive x squared like this, where our x-intercept, one is positive and one is negative, our y-intercept is going to be negative. If we have two negative x-intercepts, negative times a negative, our y-intercept is going to be positive. If we have two positive x-intercepts, okay, so that's positive times a positive, our y-intercept is positive. And if you have only one intercept, meaning you just touch the graph, you just touch the x-axis, it's gonna be hard to draw perfectly. That number times 2 is going to be positive. Same thing here. This number times 2 or times itself is positive. So there's this connection between the intercepts at the x-axis and what y-intercept you get. It has to do with the product. Again, you don't need to fully understand that. I think it just helps to know that there is a connection there. Oh man, that was long. Whew, you all are brave to stick through this. Way to go. I know we've lost some of the crowd, but you three, way to stick it out. If you watch the recording, hopefully you took a break. But if you powered through, way to go. Pause it, come back to it, rewatch it sometime. Let this stuff kind of marinate. I hope the thing I want to emphasize again is just that, like, you're not doing pure math every time. All right. When it comes to the algebra, look to use your answers, look to back solve, look to be a little more sneaky with the quadratic math you do. Look for the hidden quadratics, look for the common quadratics. And then if there's a graph, know that there's this connection between intercepts, between the roots and the C value, which is the y-intercept. Just that kind of awareness can help. I hope to see you all at some of the other free options we have out there for you, including other free GMAT prep hours that are coming up. Check out our other free content. Until then, otherwise, have a wonderful, well, I'd say a wonderful week, but have a wonderful life wherever you are. Best of luck in your studies. Let us know where we can help. See you next time.